Hello. What follows is an introduction to exponential growth. By observing certain patterns of behaviors, we can maybe learn about graphs and tables and equations that represent exponential growth. And so we start with imagining bacteria that are able to duplicate themselves every 15 minutes. So you ask the question, if there are 5 bacteria in a dish and they're allowed to multiply, how many bacteria are there going to be after a certain amount of time? And here we're supposed to look at 2 hours worth of bacteria growth. So first of all, I look at every 15 minutes, and when I make a table, I actually show each 15-minute interval so I don't get mixed up. But here I actually have X as defined as 15-minute time periods. So I have to pay attention to that. 0 15-minute time periods, there are 5 bacteria. 15 minutes later, we have 10. 15 minutes after that, we have 20, and so on. By the time I get to 2 hours, 120 minutes, I've got 1,280 bacteria. And 15 minutes after that, there's going to be over 2,500 bacteria. So we can see the growth in the beginning is not very significant, but after a very short period of time, suddenly the bacteria are taking over. You can see that on the graph because there's a very slow rate of change, relatively speaking, in the first hour. And there's a much more rapid rate of change in the second hour. And that can be observed through calculations like this. The old rate of change trick. We went from 5 to 80 bacteria in 4 15-minute intervals, which means we're getting about 19 bacteria for every 15-minute periods, and that's just over a bacterium per minute. On the other hand, in the second hour, we went from 80 to 1,280. That's an increase of 1,200 bacteria in 1 hour or 4 15-minute periods. So that's 300 bacteria every 15 minutes, or about 20 bacteria per minute. So we go from 1 to 20 bacteria per minute in just a difference of 1 hour to 2 hours. Now, the question is raised, how did we get an equation to make this figure out how many bacteria we would have later? I mean, if I want to figure out the bacteria in, say, 5 hours, I don't want to have to make a table going every 15 minutes. That would be busy work. So I start by making a table and trying to think about the calculations that I do to get simplified results. So, I mean, 0, 5, that's pretty trivial. We'll figure out what I multiply 5 by in order to get 5, and clearly that's going to be 1. But the rest of the stuff I know for sure is going to happen. 5 times 2 that's how you double after 15 minutes. That would be 10. After 15 more minutes, what we have is the original 5 times 2, that's the bacteria we had in the beginning, and then we're going to double that, and so that ends up giving us 5 times 2 squared, because 2 times 2 is 2 squared. And so then in the next stage, after 3 15-minute periods, we've already doubled twice, so that's the 2 squared, and we're going to multiply by another 2, and so in grand total, we're talking about 5 times 2 to the 3rd power. So following the pattern then, if we had 6 stages, we've doubled 5 6 times, and we can simplify the way we write it as 5 times 2 to the 6th power. It follows then that if I wanted to talk about X stages, any number of 15-minute periods, all I have to do is take 5 and then double it once for each of the 15-minute periods, and that is unknown, giving us this function equation. So, since we're talking about exponential growth, it appears to me that an exponential function is a function whose variable is an exponent, and that's what creates the significant rate of change increase over a short period of time. Now, to understand the nature of those equations a little bit better, we imagine 4 instead of 5 bacteria, but all other conditions are the same. So every 15-minute period is marked by these X's. The 5 will double and double and double, and that's where we get to the 100,000, or actually 20,480 within 3 hours. But with the 4 bacteria, we get 16,380. Now that's both very significant because we started at a small number and ended up in the tens of thousands. But we can see that if you start at a lower number, we're going to have a slightly lower increase in the number of bacteria, as evidenced by this graph. This graph shows just over an hour's worth of growth, and they start off very similar, and then there's a slight separation. But what I remember about transformations is these are both vertical stretches of y equals 2 to the x. So this one is stretched by a factor of 4, and this one is stretched by a factor of 5. So it appears as though this number here in the equation of an exponential function not only represents where we start, because those are the y-intercepts right there, but it also represents a form of a vertical stretch for y equals 2 to the x. So, to learn a little bit more about how these equations are going to work, first of all, we want to use one of the equations. So we're going to use the equation of number 2, which was 4 times 2 to the x power, and see how the equation actually works. So we can actually estimate in 3 hours how many bacteria would there be, and in 3.2 hours. And so what's interesting about this is, at the 3 hours one, that's 3 times 4 15-minute periods. That's a total of 12 stages, so x equals 12. But 3.2 hours means 3.2 15-minute periods, and therefore we end up with 12.8. And so what's interesting is, can you actually put a fraction as an exponent? I know that this is 2 times itself 12 times, but how do we reckon with the 2 times itself 12 times and then a 0.8 of a time? We have to figure that out. We'll leave that one as a curiosity for now, but maybe we'll see if we can figure out why fractions work. I know it works though, because when I put in my calculator, it does give me a number, and it's more than the number for f of 12. f of 12.8 is larger. In fact, if you look, it's significantly larger if we go from 16,000 to 28,000. It's not twice as much, but it's a lot larger. Now another question is, what if we wanted to find out a certain number of bacteria? Like, how long would it take to get 1 billion bacteria, for example? I mean, I could see the growth going really fast, so how much longer after 3 hours will it take to get to 1 billion? Now the equation I'm solving is 1 billion equals 4.2 times 2 to the x. I can imagine dividing both sides by 4, but I don't know how to solve an equation when the variable is an exponent. So at this stage, the only tool that I have available for solving this equation is the graphing calculator, or Desmos in this case. I set appropriate viewing windows so I could see 1 billion, and I set 1 billion as my y2, and then I set 4 times 2 to the x as the y1. I used the table to get a good sense of how far along the x-axis I should go. I waited until I saw the bacteria exceeding 1 billion on my table. That's how I knew to go to about 30 on my window. The intersection here is at 27.89, and if we convert that into hours, it only takes about 7 hours for there to be more than 1 billion bacteria. Now think about how significant that is, because in 3 hours there were 16,000 bacteria, but in 7 hours, just 4 hours more, we go from 16,000 to 1 billion bacteria. So there again you can see exponential growth. Nothing's happening, nothing's happening, nothing's happening, and all of a sudden burst through the roof. That's how exponential growth behaves, and that's unlike any function we've seen thus far. And just to drive the point home, the last 2 exercises we worked with functions that were doubling, and we changed the starting value. Here we're talking about getting paid 5 cents, and what's going to happen to our pay is we're going to get it tripled every day that we work. So on the second day you're going to triple the first day's pay, and on the third day you're going to triple the second day's pay, and so on. So I recognized that 15 cents after 1 day of work and 45 cents is triple that after 2 days of work. I can generate a table and go as far as I want, but I could see already by the first week I will have made $109 just in 1 day's work, plus all the other little peddly bits I got before. So how do we get an equation for this? It should be straightforward. In this case, if we understand the nature of exponential growth, we can start at a value here, and I chose 0.05 to show a nickel so that we can get our answer in dollars, and then I do triple that value, so this second number, instead of doubling, is now tripling. That changes the b value in my exponential growth equation. So just like before, we could answer questions like, how long do you have to work just to get $1 million for 1 day's pay? And it says exceed, so we need more than $1 million. I use the same intersect technique. 1 million equals 0.05 times 0.3 to the x is 1y, and the other y is 1 million. I look for the intersection, and it's 15 days. So just over 2 weeks work, all of a sudden you make $1 million for 1 day's work. In fact, the 15th day will be under $1 million, so on the 16th day there will be over $1 million in pay. And as a matter of fact, on the 16th day it turns out to be $2.1 million. When the day before it was only $700,000. So we're getting pretty wealthy pretty fast. In fact, if we worked at this for 10 weeks, we would have 3 to the 70th power, which gives me 1.25 times 10 to the 32nd power. That's a number too big for me to even fathom. So I guess we would break the economy then. And finally, this problem, if we read it from the lens of exponential growth, we're talking about one rice in the 0th stage, and then every stage for 32 stages we're going to quadruple that. Then we start with an a value of 1 and a b value of 4, so it follows the same format for exponential growth. That enables me to generate a table like this, which can show me by the 32nd square we're talking about 18 billion grains of rice just on the 32nd square. There was a quarter of that on the 31st square, and so on. And it turns out that that's going to be an extremely large amount of rice. That's more than can probably be produced in a lifetime. And we explored a little bit of that in class. So anyway, that's the introduction to exponential growth, and what I learned from this is exponential growth functions all seem to have this behavior of being really insignificant in their change and suddenly spiking out of nowhere in a very short period of time. And the b value is that multiplier. The bigger that is, the more extreme this spike becomes, and the a value just has an effect of sort of vertically stretching those graphs just a little bit.